Let's take a look at the alkylation of amines using alkyl halides or other alkyl groups with good leaving groups. So our first step in the reaction will be to notice that our nitrogen has a lone pair. So that makes the nitrogen a good nucleophile. So it will attack some alkyl group that has a leaving group in an SN2-like reaction. Well, it is SN2. And that attack will displace our leaving group. So that should give us our alkylated amine. So you probably noticed that the nitrogen already had an R group on it, already had an alkyl group attached, and that's okay. We just added another one. So in this state, we have a plus charge on the nitrogen, and the iodide will be our counterion. Now, in the presence of more amine, and there's no reason to think there was only one molecule of amine around, what we'll have, our NH2, is the ability of that amine to take away an extra proton. So we've got to do that in red. Take away the proton and leave the lone pair on the first amine. You can imagine that this kind of reaction is in equilibrium, comes and goes, and what this would give us would be our first amine, NH, with the methyl group attached. Now, if we consider that there wasn't only one molecule of methylamine, we can consider that the reaction isn't over. That is, as long as there's a lone pair on that nitrogen, we can add another amine. So the lone pair adds to the methyl group or ethyl group or whatever the alkyl group is to kick out a leaving group again. And that will give us another methyl group on that original nitrogen. Again, there's a plus charge, and the counterion would be iodide. But wait, there's more. I still have amine present. Write that in blue. It can take away an extra proton, and we'll get to our original amine, two methyl groups present. And we've returned the lone pair. But wait, there's more, because there's another lone pair again. So still methyl iodide's around. We'll add the lone pair, kick out the leaving group, and once again we have our amine, and this time there are three alkyl groups, or in this case three methyl groups attached to that nitrogen. This is called exhaustive methylation. So multiple alkylations are a problem, and those secondary alkyl halides we'll see can give us eliminations. But for the time being, this is a salt of a tertiary amine. So that is what we call exhaustive methylation or exhaustive alkylation, and it's the way that we can take an amine. I'll put an example here of another kind of amine. And if we add in, we'll just throw it in there that there's three methyl iodides. I keep using methyl iodides because they're the quickest alkyl group to write. just one CH3. It can be other alkyl groups. Let's do this in the presence of just a little bit of base. Sodium bicarbonate. It's supposed to be a 3. And then we'll have our propyl group. The nitrogen plus charge will be on it because we're going to have 1, 2, 3 methyl groups. Iodide will be the counter ion, and there's actually a 90% yield of that one. That one works quite well. So if we consider that we wanted to have alkylation with just one, a primary amine, then we should probably do exhaustive or excess ammonia. So if we come down to this reaction, we use extra ammonia with our alkyl halide, we'll be able to get just one nitrogen attached, basically because there's so much extra nitrogen and so little of the amine. And we can add that nitrogen in here. And whatever the leaving group was there, that will be the counter ion. So then this can go on, we can work that up with some mild base to take away the extra proton, and we'll have our free base left, the RCH2NH2 amine that we were expecting. So this is a way to get an amine that doesn't have it. You can get a primary amine that way. So as we mentioned before, amines can undergo elimination reactions to form alkenes. This is an example of that. If we do exhaustive methylations on this amine, we'll end up forming this compound where we have all those methyl groups on the nitrogen. And now we have a positive charge on the nitrogen, just like we did on the previous slides. So we'd have an iodide present as the counter ion since we did methyl iodide. This second step of adding the silver oxide exchanges out that I minus for an OH minus as the counter ion. And so then that counter ion can act as the base in this reaction to remove a beta proton. So we'll call this proton the beta proton on the beta carbon. So the carbon where the nitrogen is attached is the alpha carbon, next door is the beta carbon. The hydroxide removes that beta carbon, the electrons swing in a fairly standard E2 type of elimination. Fairly standard, except that the product is the least substituted alkene. But in this case it probably doesn't matter, because what we'll end up with in this is this alkene plus the trimethylamine as our second product. So then you're wondering, how can we do direct alkylation? How can we get good, because each of these cases we get over-alkylation of our amines. We had to use, unless we had to use excess ammonia. So this again is an example of our alkylation. We used excess ammonia to get our primary amine. So the better way will be called the Gabriel synthesis. It will be a way to get a good yield in an amine. So in this reaction we use the phthalimide anion, and that will attack our alkyl halide. So again, an SN2 reaction, displacing the halide, and that's why it's usually primary. That adds the alkyl group to the nitrogen. That's illustrated right here. And then we add hydrazine and heat, and we'll get our phthalimide hydrazide, because the hydrazine adds in to displace the nitrogen in the phthalimide, and that will return to us a primary amine and methylamide hydrazide. So let me give you another example of this. I can start with maybe add a bromine out here to the end, and an alkyl chain, 4 carbons long with a branch point. So then I'll add in my phthalimide anion. So phthalimide, draw that out. And putting little electrons on that is challenging. There's our, let's say it's potassium phthalimide. And now what will happen is the anion attacks and displaces the bromide, and that will give us, I'll write the phthalimide on here. And 1, 2, 3. And there's our alkyl group added to that, still a lone pair on the nitrogen. And then finally, the hydrazine. We could imagine that that nitrogen, one of those nitrogens, will probably attack the carbonyl carbon. And as we heat it up, another nitrogen will attack, and we'll end up releasing our nitrogen as we displace it in the molecule. So I could propose that something like this happens. That attacks, electrons swing out, we'd get the tetrahedral intermediate. When the electrons swing back, we can release this as a leaving group. And then the other nitrogen will also do something similar, and that's how the alkyl group gets released. And so we would leave this product then as the amine. It's going to pick up the hydrogens. So hopefully I didn't leave out any carbons in that. 1, 2, 3, 4. 1, 2, 3, 4. And so there's our product. Isopentylamine, and there's a 95% yield in that. So we should consider that when we methylate, we're creating a salt. So this, we've seen each time we methylated or alkylated, we could end up adding enough so that we would end up with a salt. So N, 3 methyl groups, and counterion of iodide in this case, and then also 2 HI are a product of that. So we can convert an amino group, which would be a poor leaving group, into a good leaving group by this exhaustive methylation, because when it leaves here, it will be neutral as it leaves. So this is what we were mentioning previously. You can do this and then exchange out your counterion, that's the iodide, with silver oxide, and that will make the hydroxide. And it's this hydroxide that served as our base Hoffman elimination. So let's come to the Hoffman elimination again. So we brought this up before. The Hoffman elimination is a way to get the alkene that is less substituted, the least substituted alkene. So let's consider that I could have this amine, and Perhaps I even have a methyl group over here. Okay, I'll add in my first step methyl iodide, excess methyl iodide, and then second step I'll add the silver oxide. That will give us the methylated amine, still a methyl group here. And now we had the iodide. This step exchanged it out for the hydroxide. So we have this counterion hanging around, which makes a good base. Now we should consider what will be the most likely product of this reaction. So in this case, I have a couple of possibilities I could take for beta protons. So I have a beta proton here and here that I could choose to take. What you should keep in mind is that the least substituted alkene is the one that should form. So you should also consider that it means you should take the hydrogen from where there are more hydrogens. And so we'd want to take the one from over here instead of the one from the other side. They're both beta hydrogens, but this one gives us the least substituted product. So we should get this alkene plus our NCH3 product. Okay, so the least substituted product comes from taking the hydrogen that is from the carbon with the most hydrogens. And so that's how we can choose. Sapling has a good problem on that. So the reaction favors an E2, but the beta hydrogen should come from the carbon that has the fewest substituents, or the carbon that has the most hydrogens on it. So there's this is another example of the regioselectivity that we would see. There's two possible hydrogens that can be taken in this reaction. So in the case of the green beta proton being removed, that would give us the Zaitsev product. Okay? And we only see about 5% of that product in this reaction. The beta proton from the blue side will give us our 1-butene, which is the Hoffman product, and that is the preferred product from this reaction. So this reaction takes a proton, a beta proton, from the carbon that has the most protons on it, leading to the least substitute. So here's a possible problem we could solve. So this problem asks us to determine what will be the product of this reaction. So first we add excess iodide. So that's shown down here, and that will add to the nitrogen the extra methyl groups. So we'll put them on here and here, replacing the hydrogen. And then we exchange out the iodide that will result in the salt with hydroxide. And as we heat that up, the hydroxide will remove one of the protons in the reaction, one of the beta protons. So again, alpha, beta. The carbon attached to the nitrogen will be alpha, one away from that will be beta. Okay, so if the hydroxide removes this beta proton in green, that should give us this product. If the hydroxide removes the beta proton in blue, that should give us this product. And we'll just double check that in a moment. And then if the proton removes the proton, the red route, that should give us a product where we would get this result. Ethylene. So 3 possible elimination routes. So of course the first product is, the green product is di-substituted. So not that product. The second product in blue is monosubstituted, a terminal alkene. And that seems really very positive until we get to the red product. The red product actually gives us the least substituted result. So removing the beta proton from out here to give us this carbon had the most hydrogens on it. I know, compare that with this one, right? It seems like this one is good too, because this one also, the blue route also had 3 protons. But the red route gives us the least substituted alkene, and so that will be the preferred route. So we should also know that we can oxidize amines, and so the reason I'm putting this in with this section is because this will lead to another elimination reaction. So if we consider the oxidation of amines, we can take any amine, oxidize it to a new compound with oxygen. So oxidation means we add bonds to oxygen. Common oxidizing agents will be the peroxide or another peroxide, metachloroperbenzoic acid. We can take secondary amines to the hydroxylamine, and then tertiary amines will go to form the amine oxide because we can only form one more bond to something. So let's consider that the N oxide, that would be the amine oxide. If we do that reaction, so I'm starting with a tertiary amine. I add maybe peroxide, H2O2, or MCPBA. That might look like ArCO3H. So any aryl per acid could work. So in this case we'll use peroxide, and we'll get our amine oxide. Oops, I changed that out. It should be a nitrogen in there. Let me just correct that. And then we'll have our H2O left over from that. So in this case, we have created our amine oxide. And what else can we do with that, you wonder? We can do a Cope elimination. So this is very much like the reaction, the Hoffman elimination, I should say, because we'll use that amine oxide with its own base to remove a beta proton. So in this reaction, the Cope elimination, it's a syn elimination, and you can kind of see why. The oxide needs to be adjacent to the hydrogen it's going to remove. So this elimination proceeds through the formation of this 5-membered ring cyclic transition state involving that amine oxide. So there's 1, 2, 3, 4, 5 members in that transition state. And it's also a beta elimination. This is alpha and beta carbons. So the Cope elimination will also follow the Hoffman rule. We're going to produce an alkene and a hydroxylamine, and it will be the beta hydrogen removed from the carbon containing the fewest other groups. So it will be giving us the least substituted or Hoffman product. If we give an example of that, we could use this example. I think I'd rather have a different pen color than yellow, and you'd rather I did too. So there's our 6-membered ring. We'll put a nitrogen over here and a methyl group here, and we already alkylated this amine to have this mixture of materials on it. We'll heat that up, and it turns out our product will be the nitrogen still attached here. I wrote that starting material wrong. Let me just correct that because it does have the oxide on it. O minus. So this will be a cope elimination because what we have here is the nitrogen, and its oxide will remove the hydrogen from a beta carbon with the most hydrogens attached. So that would give us a product where we have this result. So that would indicate that we took off this group. This gives us the least substituted product. Now you're asking yourself, so would removal of this other alkyl group. So this one should actually give you the same product. The difference between the two is that this beta proton has more hydrogens on it than this beta proton. And so that's how we know to take from the one that has more hydrogens on it. It will give us the product that will result. Even though the other one would also give us the same product, that's how we choose. So cope elimination.